Thank you very much. So yes, it's not rocket science. Are we going to take the lights down? Yep. Thank you. So we've all heard that expression before, and maybe you've heard it in this context.
What do you do? Why? I don't mean to boast, but I'm a brain surgeon. Brain surgeon? Not exactly rocket science.
So I'm not going to be talking specifically about rocket technology or rocket engineering. It's basically about how we get from A to B, how we use rockets to get us from where we are on the Earth to various points in the solar system. So I'll briefly be talking about what rockets actually do, but then spending most of the time talking about orbits, the different types of orbits, the different shapes of orbits, and looking at how we get from Earth, for instance, to Mars, and how we get from Earth to other locations in the solar system. And then I'll finish by looking at these peculiar things, these so-called parking places in the solar system, these Lagrange points where we can park spacecraft, like Gaia or the James Webb Space Telescope, for instance. So you could say that rocket science must be complicated in order to give us that particular phrase of, it's not rocket science. And there are various phrases such as, that's why I love rocket science. It might seem very complicated at first, but when you keep digging deeper, you soon realize it's even more complicated. So we'll start with looking at what rocket does. If we were to ask members of the public, what is the primary function of a rocket? Quite often you'll get the impression that people think, well, the main function of a rocket is to lift something high in the sky, to get it above the Earth's atmosphere. Well, yes, sort of, but no, not really. The main purpose of a rocket is not to lift it high in the sky. Remember, the ISS, the International Space Station, and the Hubble Space Telescope are both actually in the Earth's atmosphere. So we tend to think of things in space as being above the Earth's atmosphere, but the ISS and HST are both in the Earth's atmosphere. It's rather thin up there at 500 kilometers altitude, but it's still inside the atmosphere. To put an object into Earth orbit, it's not strictly speaking height that matters, it's horizontal speed. As long as you get the horizontal speed right, you can put things in orbit around a planet. Yes, it's not a bad idea to get as high as possible because, of course, you want to reduce the atmospheric drag, but strictly speaking, it's not necessary to go high. It is necessary to go fast in a horizontal direction, and that's the primary function of any rocket motor. This has been known about for an awful long time. Isaac Newton told us this back in, 1686, when he wrote Principia. He gave us this little cartoon, which is blown up on the right-hand side. What if you were to put a cannon on top of a mountain and fire a cannonball horizontally? If you don't fire it fast enough, it falls to the ground. If you fire it faster, it'll fall to the ground, but it'll go further. If you fire it fast enough, it'll go all the way around the planet that you happen to be on. Newton was only thinking about Earth at the time. But if you fire it fast enough, if you have enough horizontal speed, you can go into orbit. And it doesn't matter how high that mountain is, if you just, for the moment, ignore the idea of the resistance caused by moving through the Earth's atmosphere. The stronger the planet, the faster you have to go. In other words, the stronger the planet's pull, the stronger the planet's gravity, the more likely it is to fall short. So the stronger the gravity, the faster you have to move to stay in orbit. And that basic idea, the stronger the gravity, the faster you have to go, that is key to everything that's coming in this particular talk. And you could argue that it's all you really need to understand rocket science. So let's remind ourselves what rockets do. Initially vertical, but it's not long before it starts tilting over. Almost seconds, perhaps a minute or two, and it starts to tilt over because it's the horizontal speed that we need to go into orbit. So yes, it has to get off the ground, but almost as soon as it's off the ground, it starts tilting over to give us the horizontal speed that we need to put objects into orbit. If we didn't do that, if we simply had a rocket that simply goes up and doesn't give us horizontal speed, for instance, Blue Origin's New Shepard, then if it goes vertically up, once the motor is killed, it will fall straight back down again and land almost where it launched from. So in the case of New Shepard, it went up 100 kilometers and took the brave Captain Kirk into space, but as soon as it was done, it just came straight back down again. And it took about 10 minutes to do that. So if you don't have horizontal speed, your rocket is, in a sense, useless. And that is a big misconception, the fact that rockets' only purpose is to go up. Strictly speaking, not true. So let's have a look at orbits, different shapes of orbits and how things move. Whoops. Let's try that again. Yeah, there's gravity for you. So the path of an object affected only by gravity is what we mean by an orbit. It doesn't actually have to be a closed shape, but that's what we mean. The path of an object affected by gravity, just like this laser pointer. So we're all used to the idea that planets are in orbit around the sun, and in some cases we have moons in orbit around planets as well. And Kepler, many centuries ago, observed that the planets move in ellipses by making careful observations of what the planets are doing. And Newton figured out why the planets move in ellipses. It's because of the universal law of gravitation. In other words, if you have an object like the sun pulling on an object like the Earth, then when you work out the forces involved, the force depends on the two masses and the distance between them. When you calculate the forces involved, you find that the motion is an ellipse for the planets. It might look circular, but effectively they are ellipses. The actual motions can in principle be any so-called conic section, a section through a cone. So if you take a cone and slice it horizontally, you get a section that is a circle. If you take a cone and slice it at a jaunty angle, you get an ellipse, and that's what most planetary orbits are. If you take a cone and slice it parallel to one of the sides, you get a shape called a parabola. And if you take a slice at more of a vertical angle, then you get another shape called a hyperbola. So these are all just shapes that you get by slicing through a cone, hence the term conic section. And Newton showed that, in principle, any object in orbit around a sun will be one of these so-called conic sections. The ones we see are ellipses. They might look like circles, but they're usually ellipses. And a parabola and a hyperbola are, if you like, special cases. So here's all of those different shapes put together, orbiting around the sun. And when we look at these curves, circles, ellipses, parabola, hyperbola, they're also the same curves that define the shapes of mirrors that we can use to focus light in a reflecting telescope. And the reason for that is simply that the maths gives us the same set of solutions. The maths for objects orbiting a massive object are the same as the maths for working out how is light going to be reflecting off this surface to come to a focus. And so we can use circles, ellipses, parabola, and hyperbola for focusing light. They are also the shapes that determine how objects move around the sun. And we know from Kepler's work and Newton's solutions that planets follow closed elliptical orbits, as indicated here by a couple of different examples. If a comet comes into the solar system having fallen in from the Oort cloud, which is a vast distance away compared to the sort of dimensions of the Earth's orbit, then it's almost coming from infinity as far as the calculation is concerned. So a comet falling into the solar system from a long way out will follow the limit of an ellipse, which is called a parabola. You can think of a parabola, if you wish, as taking an ellipse and stretching it infinitely far. If you take an ellipse and stretch it to infinity, the shape you're left with is a parabola. Objects that enter the solar system at speed, enter and leave the solar system at speed, follow a hyperbolic orbit, an orbit that's even flatter, if you like, than a parabola. So back in 2017, there was a particular object called there was a large chunk of rock that came into the solar system in 2017, and by mapping how it moved through the solar system and the speed it was moving at, it was determined that it was a hyperbolic trajectory, and that tells us that it can't have come from the Oort cloud because it would have fallen into the solar system with a parabolic trajectory. Because this was hyperbolic, that told us that this had entered the solar system at some speed and would pass the sun and then would exit the solar system at a similar speed. So this particular object is not native to our solar system. This is an interloper that's come from some other solar system or has simply been drifting through space and happened to come through our solar system in 2017. Now, to make sure that we're all on the same page regarding how orbits work, let me just show you a little cartoon here. And imagine that we've got two hypothetical planets, a green planet and a red planet. The green planet is closer to the sun. If it's closer to the sun, it has a stronger gravitational pull. And remember what we said with the cannon on top of the mountain firing a cannonball. The stronger the gravity, the faster we have to move to stay in orbit. So because the green planet is closer to the sun, stronger gravity, which means the green planet has to move faster, and its year, the length of time it takes to go around the sun, will be shorter. By comparison, the red planet is further from the sun, so the gravitational pull is weaker. Let's just run that animation again. The gravitational pull is weaker for the red planet, and hence the red planet moves more slowly, and hence it takes longer to go round the sun, so it has a longer year, if you like. So that is key to all of rocket science and all of orbital mechanics. If you've got a strong gravitational pull, you have to move fast. If you've got a weaker gravitational pull, you can get away with moving more slowly. Now we can see that, I know that's a very busy slide, but we can see that by thinking about things that are orbiting the Earth. The ISS and the Hubble Space Telescope are really close to the Earth on this particular scale. And if we run the animation, they're going around the Earth in about 90 minutes. We've got lots of satellites out here, like the GPS satellites. They're going around the Earth in about 12 hours. And right on the outer racetrack here, we have the geosynchronous satellites that are going around the Earth in 24 hours. The closer they are, the stronger the gravitational pull, the faster they go round. And we can see that in the moons of the Earth, whether they be artificial moons or otherwise, and we can see that in all of the planets around the sun. When we plot out for the planets around the sun, their distance from the sun in astronomical units, in other words, the distance from the Earth to the sun is 1, and we plot out how long they take to go around the sun in Earth years, we find that the planets know exactly where they should be and how fast they should be moving. In other words, the planets know about the law of universal gravitation. They knew about it long before Newton discovered it. The planets knew exactly what they should be doing, and they line up perfectly in terms of how the length of time it takes to go around the sun matches precisely what it should be at their particular distance from the sun. If we just have a look at a few cartoons of what it would be like if, for instance, we had not a huge sun and a small Earth, what if we had two objects of similar size? Well, two objects of similar size, they will go round, not one around the other, they will go around their mutual center of gravity, or their center of mass, effectively the same thing, indicated by a cross in the middle there. If the two objects aren't quite the same size, then they don't follow the same sized orbits. The larger mass will go round on a smaller orbit, a smaller circle, than the smaller mass. And if we take that to extreme and again blow up the larger mass and make the smaller mass a little smaller, then it's possible that the center of mass shown by the cross might actually be inside the larger object. This can happen, there's no particular problem with that. And if we take that to the extreme and imagine the larger object is a star and the smaller object is a planet, as shown here, then even if we can't see the planet, then a small object like a planet can make a large object like a star wobble. So even if we can't see it, the large object, let me just run that animation one more time, you can see that the star actually moves, and even if we couldn't see the planet, we can still see that star move if we can see the light from that star and use spectroscopy to tell whether or not that star is wobbling or not. And that is indeed how we detect a number of different exoplanets. Now, it might seem surprising that physicists can't deal with more than two objects at a time. We can deal with the Earth going around the sun, and we can figure out what's going on. We can deal with the moon going around the Earth, and we can figure out what's going on. But as soon as there's three objects in the mix, then strictly speaking, we do not know how to solve those equations. We can make approximations, we can do simulations, and we can say, let's see what a computer makes of this. But in terms of analytically trying to write down the equations and solve them, Well, for 2 objects that's doable, but for 3 objects it doesn't give us the sort of solutions that Newton told us about 2 objects. It doesn't give us circles and ellipses and parabolas for the motion. So for instance, if we take a hypothetical system of 3 objects, it looks like they're moving in ellipses in this particular simulation. What's wrong with that? Surely that's straightforward enough. But no, let's run the simulation a little bit longer, and we realize they are definitely not moving in ellipses. When we have 3 objects, it gets way, way, way more complicated. And this is a simulation of what we would expect of 3 equal mass objects, but trying to analytically write out the equations for that is essentially impossible in the sense that we don't know how to do it. So 2 objects is easy, but 3 or more objects, basically, unless we're very careful, there are very few actual analytic solutions where we can write out the equations of motion and work out what the solutions are. So we always have to reduce problems down to 2 bodies. Let's consider the Earth around the Sun and forget the Moon. Let's consider the Moon around the Earth and forget the Sun. We can work out problems separately, but when we try and do the entire solar system at once, we can't do that analytically. We rely on computers to calculate simulations of what we think is actually going on. So let's have a think about how we get from A to B using what we know about rocket science. For instance, how do we get from Earth to Mars, and how do we get to other objects in the solar system? If we look at this little graphic, this is from 2018, the spacecraft InSight that's going from Earth to Mars. You might think that you would wait until Earth is here and Mars is there and then take the shortest distance between the 2. Well, yes, that is the shortest distance, but it needs an enormous amount of fuel compared to the most fuel-efficient way of doing it, which is to follow the pink line shown here. You leave Earth when Earth is on one side of the solar system, and you arrive at Mars when Mars has reached the other side of the solar system. It sounds like the most inefficient way of doing it because you're traveling a huge distance, but actually it needs the least fuel to do that. And if we actually follow the track itself when we leave Earth, we notice that as the spacecraft starts to approach Mars, the spacecraft is actually just a little bit ahead of Mars, and Mars is catching it up. Notice that Mars is a little bit behind, but Mars is catching up our spacecraft, which means Mars is traveling faster than our spacecraft is. In other words, when our spacecraft arrives at Mars, it's traveling too slowly to actually rendezvous with Mars. And that dictates how we do a Earth to Mars transfer. So let's just get rid of some of that complication. Let's dim that out a little bit and simplify it by just thinking about Earth in orbit around the Sun, and let's think about Mars in orbit around the Sun. Bear in mind, this is not to scale. I've made the Mars orbit quite big just to make it a little clearer what's going on. If we want to transfer from the Earth to the Sun, Earth to Mars around the Sun, we plan on having Earth at one particular point in the solar system, and we plan to arrive at Mars when it's on the opposite side of the Sun. So it's quite a long way to go, but it is fuel efficient. The path we actually follow is that ellipse. If we just temporarily take away the Earth and take away Mars, that's the path we're going to follow. It's an ellipse with the Sun at one focus and the other focus is completely empty. But that ellipse is what's going to get us to Mars. So what we need to do, instead of orbiting with the Earth, is we need to have an additional velocity to get us onto the blue path. We have to go a little bit faster so that we move a little bit outside the green path of the Earth around the Sun. So we need our rocket motors to basically accelerate our spacecraft and give it a so-called delta V, a change in its velocity, usually abbreviated to delta V. So a Hohmann transfer, as it's called, this particular blue line, we start by giving our spacecraft an extra kick. We accelerate it for perhaps a few minutes or so to give it enough acceleration to change its velocity so that instead of going around with the Earth on the green path, it starts to follow the light blue curve. And remember what we just said about when we arrive at Mars, Mars is actually traveling faster than our spacecraft. So when we get there, we have to give an additional delta V. We have to accelerate again in order to make sure we're going fast enough to keep up with Mars in its orbit around the Sun. So we need not only an acceleration to leave Earth, we also need an acceleration when we arrive at Mars. If we didn't accelerate at that point, If we just sort of went past Mars and waved at it and then didn't do anything, then we would continue to follow the blue curve as we came back to the Earth's orbit. Now that sounds like a nice idea. If we go to Mars and decide we want to chicken out or something's wrong or we don't want to land on Mars, all we do is nothing and we automatically come back to the Earth orbit. Well, that sounds very nice, but one thing we have to remember is the Earth takes about a year to go round the Sun. Mars takes about 2 years to go round the Sun, and the length of time it takes to do the blue transfer is about halfway between those. It's about 1.5 years, which means on leaving the Earth, if we come back 1.5 years later, the Earth has gone 1.5 times round the Sun, which means the Earth isn't there anymore. The Earth is now over here somewhere. So although the Hohmann transfer will bring us back to the Earth's orbit, the Earth won't be there when we get back. So that is one of the real problems with going to Mars, is you can't simply go to Mars and then immediately come back again. You have to wait for months until Mars and Earth are in the right orbital positions to do another Hohmann transfer to get you back again. So it takes many months to get to Mars. You then have to stay on Mars for many months, and then you spend many months on the transfer back again. That's why Mars missions are not going to be a few weeks. They are going to be typically years. And so if we want astronauts to survive that, we have to make sure that they are able to survive the radiation in space and on the surface of Mars for years, not simply a few months. What about getting to other planets? In principle, we could do the same thing. In principle, we can do a Hohmann transfer from Earth to any other planet in the solar system. But in the 1960s, it was realized that there's a more sensible way to do this, a more efficient way to do it, a so-called slingshot, sometimes called a flyby, but strictly speaking, they ought to be called gravity assists. So it was realized in the 1960s that there would be opportunities in the 70s, 80s, and 90s to do a gravity assist and actually use the gravity of planets to help you get over these vast distances, especially in the outer part of the solar system. Given that the planets are so far apart in the outer part of the solar system, the idea of having an assist from the gravity of a big planet like Jupiter or Saturn, that means that you can save on fuel and you can get to your destination much faster and much cheaper because your rocket motor doesn't have to be as large. In effect, what's happening is that by flying past a planet, you can actually rob that planet of some of its momentum and give that momentum to the spacecraft. But how does that work? Because if we think of a very simple analogy of, let's say, here on Earth, we have a ball rolling from a hill down into a valley, and there's a hill on the other side of the valley as well. If that ball is just resting at the top of the hill and we just give it a nudge, it'll fall and it'll roll down the hill, and it'll accelerate. Let's for the moment just forget about friction and forget about air resistance and just assume that there's no other factors in here other than gravity, which will be accelerating the ball as it falls from the hill into the valley. So it'll pick up speed and it'll get faster and faster, and its maximum speed will be as it goes through the bottom part of the valley. After it's gone through the bottom of the valley, it will then start climbing the hill on the other side. And of course, as it climbs the hill on the other side, it'll start to lose speed. So it'll be picking up speed as it comes in and losing speed as it goes up the other side. And if the second hill is the same height, it'll end up just reaching the top of the second hill. But what's actually interesting, at least from a physics perspective, is that if you think about the object at the same height, it will have the same speed. In other words, it doesn't matter how high this bar is set, at a particular height on the way in, it'll have exactly the same speed on the way out. It doesn't even matter what the shape of the hill is. It doesn't matter if it's a smooth curve as I've shown here, or whether it's got some bumps along the way. The idea that the speed on the way in is exactly the same as the speed on the way out at the same height will apply regardless of the shape of the hills and the valleys we're dealing with. So if that's the case, then when we're dealing with flying past an object like, let's say, Jupiter, for instance, as we're coming in, we're sort of falling into Jupiter's gravity well, and then we're coming up the other side, just like falling into the valley and coming up the other side of the valley. So the maximum speed, the maximum flyby speed, will be the closest approach to Jupiter. So we can imagine coming in on our way into Jupiter and accelerating as we get closer and closer to Jupiter. But then once we've passed the closest point and we're going up the hill on the other side, whatever speed we gain on the way in, we will lose on the way out, because it's just like going from a hill through a valley and up the other side, as we've just shown in the last little cartoon. So if whatever we gain on the way in, we lose on the way out, how can gravity assists ever get us faster from A to B? And here's the clever bit that was worked out in the 1960s and indeed probably earlier. The inward speed and the outward speed are the same relative to Jupiter. As far as Jupiter is concerned, the object is coming in and going out at the same speed. But Jupiter itself is moving relative to the Sun. It's going round the Sun. We can imagine the Sun is somewhere way off to the top left of this cartoon. So the inward speed and the outward speed relative to Jupiter are the same. But if you can arrange it, that the outward speed, if you can arrange the geometry of your flyby such that the outward trajectory, the outward motion, is in the direction that Jupiter is going, then this outward speed is relative to Jupiter, and Jupiter is going that way, which means you go even faster in that direction. So relative to the Sun, it might be that you come in at 10 kilometers a second, but you might manage to leave at 25 kilometers a second relative to the Sun, simply because you're picking up that additional speed that Jupiter is moving at, and the idea of inward and outward speed are relative to Jupiter. So you can see that you can gain an enormous kick by flying past a planet as long as you arrange the geometry appropriately. And that's what NASA engineers do, is they try and compute where do I have to go in order to get the maximum kick to get me from where I am to where I want to be. And that was first implemented in 1972 with Pioneer 10 going to the outer planets when Pioneer 10 visited Jupiter. And if we see again the trajectory, the pink is the spacecraft. It's coming towards Jupiter at about 10 kilometers per second, but once it's done the flyby, the speed suddenly jumps to 20-something kilometers a second. And notice the change in direction. It came in one direction and took a dog leg to the left and is now flying out of the solar system. Let's watch that one more time. It approaches Jupiter relatively slowly, but then it gets a kick and a most noticeable adjustment to its direction of motion. And it's now going fast enough to leave the solar system. So Pioneer 10 was the first spacecraft we launched, which we ended up giving enough velocity to leave the solar system. Pioneer 11 did the same sort of thing, but with Pioneer 11, they wanted to visit Saturn. And in principle, you can go directly to Saturn, but that needs quite a large rocket burning a lot of fuel to give you the velocity to get there. So they decided that they would head to Jupiter first, even though Jupiter is in the wrong direction. They went to Jupiter first, and they fired off the spacecraft, which did a flyby of Jupiter. Look at the change of direction there. It took a 90-degree turn to the left virtually, and then the spacecraft goes flying off all the way to the other side of the solar system for its encounter with Saturn, to get our first close-up views of Saturn and the ring system. So there it is once again, heading for Jupiter. It does a flyby of Jupiter, gets a few more pictures, but the main purpose was to give it enough of a kick to get it out to Saturn without expending any more fuel. And once it arrived at Saturn, it took its pictures, etc. Notice another flyby produces another kick. It's already going fast enough to leave the solar system. That just gave it a little more velocity. So Pioneer 10 ends up leaving the solar system rather faster than Pioneer 10 is leaving the solar system. We can see the same sort of thing happens with Voyager in 1977, the launch from Earth heading in the direction of Jupiter. It did a flyby of Jupiter, picked up a bit of extra speed, another dog leg to the left, and the main mission for Voyager 1 was to look at Saturn and in particular Titan, because it's known that Titan has an atmosphere, and so it was a mission priority to get as close to Titan as possible. And because of the timing of how the moons were moving around the planet, it was not possible to do a close flyby of Saturn. So we definitely pick up a lot of velocity here at Jupiter, but notice that when we pass Saturn, no kick, no extra velocity, no kink in the trajectory, because they sacrificed the fact that they could have picked up more velocity by doing a flyby of Saturn, but the priority was to look at Titan, and so they took a slightly different trajectory as they went through the Saturn system. With Voyager 2, which was following on close behind, it was launched a few days earlier, but on a slightly different trajectory. It ended up arriving at Jupiter and Saturn sometime later. But because Voyager 1 had already looked at Titan, that was no longer a mission parameter. And so now it was possible to do a flyby of Jupiter and then use Saturn to give you a kick towards Uranus and Neptune. And look how beautifully they are placed in the solar system to allow you to do this grand tour of all of the outer planets. That's what was realized in the 60s, and the calculations were done and the timing was calculated such that Jupiter and then Saturn would then give a kick that would take you on to Uranus, which would then give you another kick, which would then take you to Neptune. They actually flew over the pole of Neptune. These little tick marks indicate that the purple line is actually below the plane of this diagram. It's below the plane of the ecliptic, because it was chosen to go above the north pole of Neptune to give a better view of what's going on. And as it went over the pole of Neptune, it got a kick downwards and started to dive below the ecliptic. Notice it didn't do a kink to the left or the right. It, in effect, gave a kink slightly downward. If we actually look at how fast Voyager 2, if we take that as an example, as a function of its distance from the Sun, again in astronomical units and in multiples of the distance between the Earth and the Sun, if we look at the speed relative to the Sun, it started at a velocity of about 35 or so kilometers a second, but as the spacecraft moved away from the Sun, it started to slow down until it reached Jupiter, at which point it got a kick, and then another kick from Saturn, and again from Uranus, and again from Neptune. Notice that the Jupiter kick is large because Jupiter's a huge planet. It also seems a bit odd, but look at the kick from Neptune. It originally accelerates, but by the time it leaves Neptune, it's actually moving slightly slower because it was not a priority to gain speed for Neptune. The priority was go over the pole and see if we can see as much as possible of the planet. So the fact that it lost a bit doesn't really matter, because the amount of speed you need to leave the solar system is indicated by that blue line. In other words, when the spacecraft gets to Jupiter, it's not moving fast enough to leave the solar system. But after we've had the gravity assist from Jupiter, even though it gives a big kick and then slows down a little bit, the red line is above the blue line. The red line is sufficient to leave the solar system. And it doesn't matter what we do with the next planets. Saturn makes it go faster, Uranus makes it go faster, Neptune slows it down a little bit, but it doesn't matter. The red line, from this point onwards, the red line is always above the blue line. So from this point onwards, this object is going to leave the solar system. And in fact, Voyager 2 is basically the fastest object that is now leaving the solar system. So using gravity assists to help us cover these enormous distances, especially between the outer planets, that makes perfect sense. But what's not quite so widely recognized is that the idea of gravity assists also works when we're trying to get to the inner planets. For instance, Bepi-Colombo, which will be in orbit around Mercury in 2025, it's gone past the Earth, past Venus, and past Mercury, and each time it goes past, they've tried to arrange the geometry such that they don't get an additional delta V to make it go faster. They've arranged the flybys to try and reduce speed, because otherwise, when you fall from the Earth into the inner solar system of Mercury and Venus, you're going too fast. You need to put the brakes on and slow down a bit. So a planet flyby can be used to lose speed, and in the case of Bepi-Colombo, it's already done flybys in 2020 of Earth and 2020 of Venus and 2021 of Venus a second time, and in 2021 Mercury, and it will continue to do flybys of Mercury, each time slowing down just a little bit without using any fuel, just using the gravity of the planets, in order to sync up with Mercury so that it can eventually drop into orbit. So a flyby, a gravity assist, works both ways. It can increase or decrease your velocity. It can accelerate or decelerate the spacecraft depending on how you arrange the geometry of the flyby. But in all cases, it's done because it saves fuel. You don't have to fire a rocket motor to increase your speed or decrease your speed. So that's why gravity assists are so useful. It might, in principle, take longer to get to where you want to go, but if you don't use fuel, you don't need as big a rocket, you don't need to take as much fuel with you. You can take more instrumentation, more cameras, more spectrometers. You can do more science by taking less fuel with you. When you get to a particular place, for instance, if you go to Saturn, you might want to go into orbit around Saturn because you might be interested in watching the planet and watching the rings. And in some cases, you will need to expend some fuel. So these are the orbits of Cassini around Saturn between those dates, 2004 and 2017. Just to show you how complicated that is, let's just spin it. You can see that the orbits that the spacecraft went in were very complicated. It kept changing orbits in order to get different views of the planet it was studying. But each time it changes orbit from one shape that looks a little bit like an ellipse to another, every time you change orbit, you need to burn a little bit of fuel. So missions like this take enough fuel with them to give them a nudge to put them into different orbits, but when your fuel runs out, you no longer have any control of your spacecraft, and effectively your mission comes to an end. So any orbital changes are going to be influencing the mission lifetime. And that's something you have to calculate. Whenever you put any spacecraft up into space, you have to think, how much fuel am I going to give it? Because ultimately that will dictate the mission lifetime. So let me finish with this idea of parking a spacecraft somewhere up there such that we can minimize what we need to do to get it to stay in one place. The Earth, of course, is going around the Sun, but basically if we placed an object anywhere in space, it would either fall towards the Earth or fall towards the Sun, or we would have to keep it moving with the Earth. So what's this idea of a Lagrange point? Coming back to this picture, let's just remind you that the key observation is that the closer you are to the Sun, the stronger the gravitational pull, and if you have a strong gravitational pull, you have to move faster to stay in your orbit. So there's the green planet closer to the Sun. It has to move faster in order to stay in that orbit. The red planet here, or the red object, is further from the Sun, weaker gravitational pull, so it can move more slowly. That is the key observation that helps us understand what Lagrange points are all about. So these little yellow arrows here are supposed to represent the fact that the green object, whatever it might be, is feeling a stronger gravitational pull to the Sun than the red object, simply because the red object is further away from the Sun. Greater distance, less force. Is that always the case? Well, if we're only considering, for instance, two planets and the Sun, then that is indeed the case. We can't change the gravitational pull of the Sun, but we can be clever about how we arrange the orbits. We can arrange it so that an object in the red orbit, let's assume that the green is Earth and the red is an object we're interested in, we can arrange it so that the red object feels an additional gravitational force. So for instance, let's take this example. Let's assume that green is the Earth and it has a period of exactly 1 year. It goes around the Sun in 1 year. The red object, whatever it may be, will take longer to go round the Sun because it's further from the Sun, weaker pull, so it'll go slower, and it will take more than a year to go round the Sun. But what if we could arrange it that the red object is close enough so that it's pulled not just by the Sun, but it's given a tug by the Earth as well? In other words, the red object is pulled by the Sun, the yellow arrow, but it's also pulled to the Earth, the green arrow. Let's arrange that so they're pulling in the same direction. We can calculate, if we so wish, that there is such an orbit. There is a red orbit that's at just the right distance so that the extra pull from the Earth, the extra green arrow, is just enough to increase the gravitational pull. So instead of going round in a year and a bit, this object goes round in a year, the same as the Earth. So if the red object goes round in a year, what would that look like? Well, they would go round together. And the Earth would always be in the same direction as the Sun. As seen from the red object, The Earth and the Sun are always in the same direction, so they're always pulling in the same direction, so the red object will go round in 1 year, just like the Earth. So, if we have that situation, if we have the red object, which can only work at a certain distance from the Earth, we can only do this if this distance is just right so that the extra pull from the Earth means that the red object goes round in a year, just like the Earth does. But that is precisely what we mean by a Lagrange point. That point is called L2. L2 is a point on the line from the Sun to the Earth and keep on going. You arrive at a point such that the gravitational pull of the Sun and the Earth means that L2 goes round in 1 year, just like the Earth goes round the Sun in 1 year. Now, these distances are quite definitely not to scale in this diagram because the distance from the Earth to the Sun is 1 astronomical unit, and the distance from the Earth to the L2 point is approximately 1/100th of that, 1% of the distance between the Sun and the Earth. So quite definitely not to scale. And it just so happens that if this distance is about 93 million miles, then the distance from the Earth to L2 is in the ballpark of 1 million miles, roughly speaking. The idea is conceptually the same for L1, except that L1, the Lagrange point labeled L1, is inside the Earth's orbit. Now L1 is being pulled towards the Sun in one direction, but being pulled towards the Earth in the other direction. So the gravitational pull on L1 is less than you would expect in the absence of the Earth. So although an inner orbit would be expected to go round faster, just like Venus and Mercury go round the Sun faster than the Earth does, because the pull on L1 is now reduced because of these pulls in different directions, then again, L1 goes round the Sun in 1 year. So L1 is, if you like, fixed in space relative to the Earth and the Sun. As seen from the Earth, L1 appears to be always in the same position. It always seems to be in the same direction as the Sun, always in the same distance. Again, not to scale because the Sun to Earth distance is of AU, and roughly speaking, the distance from L1 to Earth is very similar to the distance from Earth to L2. They're not quite the same, but they're very similar. It's about 1% of that distance. So L1 is a very good place to park spacecraft if you want to observe the Sun, for instance, because if you put a spacecraft there, in principle it doesn't go anywhere. It goes round the Sun in 1 year just like the Earth does, which means the Earth never gets in the way. It's always close to Earth, it's only 1 million miles away, and the Earth never gets in the way of your observations. Now, how do we work out where these Lagrange points are? Well, we know how gravity works. Newton told us how gravity works. The gravitational force between two objects only depends on the mass of those two objects and the distance between them. And we know exactly how that works. We've known that for 400 years. So that's the equation we have to solve. It's easy. All we do is to say, well, we've got the mass of the Sun and the Earth and the distance from the Earth to the Sun and the Earth to the L2 point. We just solve for R. And I'm sure you can all do that, yes? Okay, yes, I did say it's not that hard if you just skip the maths, so maybe we ought to skip the maths. Yes, we can work it out, but we don't have to in order to understand that the existence of Lagrange points are only based on the idea that if we increase the gravitational pull, we can get these Lagrange points to move around with the Earth. It turns out, we're not going to do the maths, but it turns out there are actually 5 places where you can park a spacecraft. L2 beyond the Earth, L1 inside the orbit of the Earth. There is another one, a sort of counter-Earth location on the other side of the Sun from the Earth called L3, and there are 2 at 60 degrees in the orbit there called L4 and L5. Now, L2 is particularly interesting for a number of different reasons. If you're at L2, then a relatively modest-sized sun shield can block the light from the Earth and from the Moon and from the Sun. And you don't need to keep shifting that sun shield. If you were in an arbitrary point in space, then the Earth and the Moon and the Sun might be in different parts of the sky, and so it would be very difficult to block off the light from those 3 objects. But if you're sitting at L2, all of those 3 objects are always in the same direction, and so a sun shield can block out everything from this side and gives you an uninterrupted view of the sky to the right, if you like, of this particular diagram. Now, L2 is actually in Earth's shadow. You can perhaps see that depending on the size of the sun and the distances. Again, this is not to scale, but the sun will cast a shadow from the Earth, and Earth's shadow will extend into space beyond the orbit of the moon. And in fact, if you were to sit actually at L2, you would find yourself in a state of permanent eclipse. So if you've got solar panels on your spacecraft and you want to use the energy from the sun, you wouldn't actually sit actually at L2. It's preferred that you actually do a little orbit around L2. So spacecraft such as Gaia and now the James Webb Space Telescope, which has joined Gaia, they are both orbiting around L2. There's actually plenty of space out there. They're never going to get close to each other. They're both going around this point in space called L2, this parking zone, if you like. Now, if a spacecraft moves away from L2, it tends to get pulled back. In other words, if an object was placed close to the red dot and tended to drift upwards, then the pull of the Earth would tend to pull it back down again. And if an object close to that red dot tended to drift downwards, then the pull of the Earth would pull it back up again. So those green arrows show you that any motion of the spacecraft would tend to automatically get corrected. In other words, we don't have to keep firing our rocket engine to keep us on the red dot. If we drifted up or down in this particular diagram, then the pull of the Earth would automatically bring us back to where we wanted to be. Unfortunately, it doesn't work the other way. If the object started to drift towards the Earth, it would continue to drift towards the Earth. If it started to drift away from the Earth, it would continue to drift away from the Earth. In other words, there is not a self-correcting way of keeping the spacecraft there. So we do have to use a little bit of fuel, because otherwise, when it drifted towards the Earth, it would keep drifting. We would need to use a little bit of fuel to keep us there. And one way of visualizing that is to think about this sort of donut, if you like. The ability of a spacecraft to park at a Lagrange point can be visualized according to this sort of diagram. Let me tell you what this is supposed to be. If you imagine that these contours here are like contours of height, imagine this is an Ordnance Survey map, and we're looking at contours of height, and we're thinking about an object that wants to roll downhill. These are high points, and these are high points, and we can imagine what's going on around L2 that will help us understand what's going to happen to an object if we think about a ball bearing placed on this surface and rolling downhill. So let's look a little more closely at what's going on between the Earth and the L2 point. Let's just blow that up a little bit. So these are high contours at the top, high contours at the bottom, and these are low contours surrounding the Earth. But look at what's going on around the L1 point, the L2 point. The arrows are showing the direction of downhill. If you simply look at the colors of the contours and start following them, you can see downhill points towards L2 from above, and downhill points towards L2 from the bottom. But when we think about going left-right in this particular diagram, downhill is pointing to the left and downhill is pointing to the right. So L2 is not a hilltop, because on a hilltop, down would be any direction you choose. If you were in a well, up would be in any direction you choose. So L2 is not a hilltop, L2 is not a well. Downhill is away from L2 in those directions, but towards L2 in the other two directions. So if it's not a hill and it's not a well, what is it? It's a saddle point, or, if you're not a mathematician, it's a Pringle. The James Webb Space Telescope is parked at a Pringle. You're not going to forget that now, are you? So in one direction is up, and in the other direction is down. That's what a saddle point means. Depending on which direction you go, it's either uphill or downhill. It's not a well, and it's not a hill. It's a saddle point. And so when we park a spacecraft there, again, we're not actually sitting actually at that red point. We're doing a little dance around it, a little orbit around it. But going up and down in this diagram, or around this orbit, in the case of an object like the James Webb Space Telescope, the Earth will automatically keep it going in that orbit. But if we do start to drift towards the Earth, we will have to do a little bit of station keeping. And how much fuel we need to use to do that station keeping will depend on how precisely we placed the object in orbit around L2. The people who launched the James Webb did just such a fantastic job of getting it exactly where it needed to be. It's thought that enough fuel was saved to extend its mission by maybe 5 or 10 years, because all they're going to need to do, they hope, is to give it the smallest of nudges every few months. It'll continue orbiting L2, the Earth will keep it in that position, or I should say, I suppose, the combined gravity of the Sun and the Earth will keep it in that position, and it will slowly drift towards the Earth, and every few months they'll fire the rocket motors and just give it a nudge back again. And then it will continue orbiting L2 for months and months and months. It'll slowly drift towards the Earth. Every once in a while, they'll just give it another kick to bring it back to its correct position. And if you get that orbit right, you need the smallest of nudges, which needs the smallest amount of fuel, which means your fuel will simply last longer. So that will always be the case for any object placed at L2 or L1. You'll always need to do a little bit of station keeping, but if you get it right, you can minimize that to extend your mission lifetime. Let me just say one or two words about the other L points. L1 is useful for looking at the Sun. L3 has no benefit whatsoever as far as we can tell. It's on the other side of the Sun. You can't see it. You can't communicate with it. In principle, you can bounce signals around, but nobody yet has found a good reason for putting anything at L3. L4 and L5 are sometimes occupied. For instance, there are asteroids at Jupiter's L4 and L5 point. If we come back to that donut, made a little bit fainter here, the L4 and the L5 point, which are on the radius, on the same orbit as the planet in question, there are little orbits in these little contours, if you like. It's possible for objects to do little orbits around L4 and L5. They can't stray too far from them, otherwise the gravity gets disrupted and they'll fall either towards the Sun or away from the Sun. But small objects can be caught in orbit around the L4 and the L5 point. Well, Earth doesn't have that much gravity in terms of the strength of Earth's gravity, so there isn't actually anything interesting at L4 and L5 as far as the Earth's orbit is concerned. There's just thought to be a little bit of dust there. That's about it. But Jupiter's gravity is a lot stronger, so at the equivalent points, and every planet, every object in the solar system will have its own version of L1, L2, L3, L4, L5. So at the L4 and L5 point of Jupiter's orbit, because Jupiter has such a strong gravity, then it is possible for small objects to be caught at the L4 and the L5 point. And that's precisely what has happened over the last few million or billion years. Lots of little asteroids have been caught at these 2 points, and these asteroids are called the Trojan asteroids. In principle, they could be similar objects for any planet, but you tend to have relatively strong gravity to hold on to big chunks of rock. Some orbits do look really weird. We know that Newton tells us that if you've got one object orbiting another, it'll be a circle or an ellipse or possibly a parabola or a hyperbola for the shape of the orbit. But when we're talking about two objects like the Earth and the Sun, and then we consider what's happening to a third object, which is moving with the Earth as the Earth goes round the Sun, then we can get some really odd results. So these contours that are shown by this does the ball roll downhill sort of map tells us that it is possible for an object to follow a really weird looking orbit. In other words, if we follow the arrows, it can actually travel towards the Earth. It gets pulled towards the Earth, which pulls it a little bit closer to the Sun. But if it gets closer to the Sun, it goes around the Sun faster, which means it gets ahead of the Earth and follows around here. And as it comes here, it gets tugged by the Earth, which pulls it out. Now it's outside the orbit of the Earth, which means it's going slower, which means it goes around here. So it looks really, really weird, but it still follows the same rules. It still follows the rules that when closer to the Sun, it goes faster, and when further from the Sun, it goes slower, relative to the Earth. Remember, all of this is as seen from the Earth. It makes a lot more sense when we see both of them going around the Sun. But still, we can think about these so-called horseshoe orbits, and we do actually see objects in horseshoe orbits. For instance, some of the moons of Saturn seem to do this little dance and go in this rather weird-looking structure. So All it is obeying the rules that we established right at the start. Stronger gravity means faster motion, and it can lead to some odd results depending on how you plot them on a piece of paper. But there's nothing magic, there's nothing peculiar about that, it's just an odd way of representing it. And I said at the beginning that an orbit is just the path of an object under the influence of gravity. Strictly speaking, they don't have to be closed orbits. We know, for instance, circles and ellipses are closed orbits in our solar system, and we know that hyperbola are open orbits. But if you take, for instance, this rather hypothetical and highly contrived example of what if we were to take three equal mass objects and move them in such a way that they move towards each other, how might they behave if we just take what we understand from gravity? The gravitational force just depends on the masses and their distance between them. These three objects move in a way which is quite odd and at first sight really, really weird, because what they do as they fall towards each other, they don't travel in circles, they don't travel in ellipses, they stop and then like a roller coaster they come backwards and follow exactly the same path again. So three objects, if you could get three identical masses and start them at the right place and start them in the right direction with the right velocity, they would follow those three orbits, which looks absolutely crazy, but that is perfectly okay according to Newton's laws of motion. Is it possible for a triple star to do that? Well, no, because you could never start that motion with three stars in just the right place with just the right motion. If you were to start in different places with different velocities, you would get a mess like the three-body problem I showed you earlier. But it's interesting to note that you don't have to think of orbits as just being circles, ellipses, and parabola, for instance. And don't get me started on orbits around black holes. When you've got a black hole, space is so distorted that Newtonian mechanics no longer applies. And so far from having ellipses or circles, you don't even get the same path twice. It just seems to be absolutely crazy. It looks entirely chaotic. It can be calculated if you understand what the black hole is doing, but because space is no longer flat, space is now extremely warped in the environment of a black hole, you can't expect to get the sort of solutions that we know and love from Newtonian mechanics. So I've been talking about what rockets do and looking at orbits. For those that are interested, I've got Buzz Aldrin here because Kepler established that planets move in ellipses. Newton told us why they move in ellipses, and Buzz Aldrin seemed to have an innate ability to understand orbits just by thinking about them. His doctorate was in orbital mechanics, and he was able to think about how one object rendezvous with another, like, for instance, a command module and a lunar module in orbit. He had an ability to think through problems and visualize how these things actually worked. I've told you about how we get from A to B in terms of how we get from Earth to Mars, and how we can use gravity assist to get to the other planets in the solar system, either by increasing our velocity to get to the outer planets or decreasing our velocity to get to the inner planets. And then I said something about how the fact that there are various parking places around the Earth and indeed around other planets in the solar system where we can park spacecraft, and indeed have done for a number of different spacecraft such as Gaia and the James Webb Space Telescope. So why is rocket science considered to be so hard? Well, partly because of the maths I showed you earlier, that even just something as simple as calculating where is L2, that's not necessarily something that's easy to do. Yes, I admit that there are some objects in the solar system that move in ways that are, at first sight, not very intuitive. We can't expect everything to just go round the sun in circles. Even if the maths is relatively straightforward, we still end up with some pretty weird-looking orbits. And I agree that rocket science can be considered hard, and yes, calculating how to put the James Webb into orbit around L2, that is not a trivial thing to do, especially when you consider the phenomenal accuracy that they actually ended up with, placing it pretty much spot on where they wanted it to be. So although in principle we can write out the equations, getting it all right to the precision we need to actually send spacecraft out into the solar system is truly phenomenal. And yet the underlying idea is totally straightforward. Stronger gravitational pull leads to faster motion. The Earth moves around the sun faster than Mars. That is it in a nutshell. Everything else is just maths. Because, after all, it's not rocket science. Thank you all very much. Has anybody else noticed that the sleigh is very similar to the James Webb?